All right. Hi, everyone. I am Alex Andoni from Columbia University, and I'll be talking about edit distance, and in particular, computing approximating edit distance in nonlinear time. And it's a great pleasure to give it at the ICPC University Lecture Series. I used to be a competitor long time ago, not necessarily too successfully, but that was kind of one of the reasons for kind of the competitions is one of the reasons that I started working on this problem. Okay, so what is edit distance? I'm sure many of you have seen this before early on. This is a problem of computing a distance or similarity or dissimilarity measure between two strings. Okay, so here we given two strings, x and y, of length n, and they come from an alphabet sigma. Okay, and the edit distance between two strings x and y is just the minimum number of insertions, deletions, and substitutions to transform x into y. Okay, so this is introduced by Damirao, and this particular version is called Levenstein distance. Here's an example. We have banana and ananas, two words, and the distance here is 2 because we can delete b from banana and insert s, and this way we transform banana into ananas. Okay, and this distance has a lot of applications in many areas in bioinformatics, where you would probably be comparing perhaps not the words but the genetic codes of these fruits, just to kind of measure how similar these genetic codes are. Okay, and it has many applications in our areas: linguistics, natural language processing, and so forth. Okay, but as I already, I guess, alluded to, right? I mean, part of the our motivation for studying this problem, right, and it's also partly kind of perhaps personal motivation as well, is this is a very, very classic example of dynamic programming. This could be actually the first one. The first dynamic programming that I learned personally when I was preparing for competitions back in 90s, and that was blew my mind, kind of, right? Like we can do such cool algorithms. Okay, and it appears in standard algorithms, introduction to algorithms, right? I teach it in my class of introduction to algorithms and so forth, right? And this classic dynamic programming algorithm runs in quadratic time, right? It's due to Wagner-Fisher feature, and even though kind of early versions appeared as well, and it's basically based on you build a table which is n by n, and you fill it out with numbers, which is basically the distance between prefixes of these words, and you fill it using this kind of recursive formula, which you can just basically build it by kind of traversing the array. And it's cool, kind of, right? I mean, this is very classic. But of course, the question is, and here in the right bottom corner, you can read out the answer, which is that the edit distance between these two strings is 2. Okay, but of course, the question is, okay, quadratic time, it's good, it's polynomial time. But especially nowadays, right? We think of n as being large, and we want to save time whenever it's possible, and even when n is small, right? But especially when n is very large, think about kind of in billions, and then n squared becomes basically prohibitive, right? So it is very natural kind of to ask the question: well, can we do this faster? Can we improve upon this quadratic time, and maybe get runtime which is closer to like sorting like n log n? Right? Okay, so what do we know, right? So this problem of computing the edit distance, in particular faster than quadratic time, has been open for many decades, and people have studied. And the best algorithm today is due to Massick-Patterson from 1980, which improves this by basically log squared n factor. Okay, so not too much really. Okay, and this is using a technique called Russian technique, which is useful for our problems, but it basically improves the runtime by logarithmic factors. Okay, so can we substantially speed up computation of edit distance? Okay, and indeed this problem has been studied, and there is some progress and some very nice algorithms for special situations, in a sense, right? Think about I guess one of the famous algorithms is due to Konin and Myers, who showed basically this kind of runtime, which is basically faster than quadratic when any distance is sufficiently small. Okay, so let's say when it is at most root n, then the distance is small, then you run in almost linear time. Okay, and also things like average case, random case, pseudo-random cases. we know better algorithms, right? But for the kind of vanilla version, there's nothing kind of else guaranteed. We don't really know better than Massey Patterson, and in fact, kind of recent research, kind of more on complexity side, especially in particular coming from the relatively modern area of fine-grained complexity, have basically suggested that we shouldn't hope for a faster than quadratic time algorithm unless we break a hypothesis called the strong exponential time hypothesis, which you should think about as a strong version of P not equal to MP problem. Okay, it's not as likely as the fact that P is not equal to MP. There are some researchers who think, maybe Ceph is actually not true, but it would be a big problem to solve, kind of, to break these Ceph conjectures. So, barring that, we shouldn't hope for less than quadratic time algorithm. Okay, so, what do you do? Kind of like, well, move on to a different problem, or you can ask, say, well, I still need to solve this problem. I still need to run in, relatively fast. What is the best thing I can do? Okay, so another kind of perspective is to say, well, can we approximate this? Can we approximate the distance, right? So, so just like approximation algorithms, have been kind of a way to tackle problems which were NP hard, like the SP problem, for example, and we wanted to solve them in polynomial time up to approximation. Here as well, we can ask the same kind of type of question, saying like, well, can we approximate the distance? Okay, in time which is less than quadratic. Okay, so there have been kind of two waves of results, right? So one was basically 2000s to 2010s roughly, and there the best result was that in near linear time, where here I'll mean this by time which is n to 1 plus epsilon, we can get polylogarithmic approximation. So basically log to 1 over epsilon essentially. Okay, so this is kind of the result of 2000s, right? And then in 2018, came kind of a big breakthrough, and by Chakraborty, Das, Goldenberg, Koucky, and Sachs, who showed that you can achieve a constant factor approximation in time, which is this n to 1.6 roughly, which is sub-quadratic. Okay, so this was a big breakthrough. It opened best paper. It won best paper award at Fox, and has led to much more research. In particular, the natural question, kind of after this paper is like, well, can we improve this runtime faster? Can we improve it and get, in particular, near linear time still with constant factor approximation? I should say that an independent work has obtained an algorithm that also achieves constant factor approximation still in sub-quadratic time, but for quantum algorithms. Okay, and some ideas actually intersect between these papers, but not all. And afraid there is one component of basically this paper that is kind of classic, right? Whereas this component here is quantum. Okay, and by the way, all the I won't read the citations because it takes time, but there will be a link at the end of the talk where you can look up the citations if you're curious to take a look at the which papers I really mean. Okay, all right, so. Okay, going back to the quest of fastest algorithm for edit distance that achieves constant factor approximation. Okay, what do we know? So in 2020, there are a couple more papers that improved the runtime to basically near linear, to what we would like. But in a sense, with a caveat, right? The caveat is that it only it achieves constant factor approximation, but also has an additive approximation. But additive approximation is relatively close to linear. Think about this as this is like a little bit the opposite of Ukonian and Meyer's algorithms, where those were kind of fast when the edit distance is small. These latest two algorithms basically said that as long as your edit distance is actually very large, is very close to linear, you can approximate it. Okay, so this is how you should read this result. Okay, and basically in also last year, together with my student Negev Shekel Nosatzki, we obtained an algorithm that basically in some sense removed that caveat, but basically achieved what we wanted to achieve here, namely we can obtain runtime which is n to 1 plus epsilon with constant factor approximation. Okay, So this is kind of our result. And I should mention that I will talk about kind of general ideas that went into this, the second wave of the results for edit distance, and probably mostly the techniques that came from Chakraborty et al. Paper, but also some ideas from other papers, and while kind of perhaps it sounded like I'm suggesting it's like, okay, and we are done, it's like, we've completed constant factor approximation, new linear time. We are not. The last slide, I'll mention, many open problems that remain here. Okay, so, and yeah, this is very cool problem to work on. And, yeah, I've been working for quite a number of years. So very happy that we got this result. So let me describe you the ideas that go into basically mostly the results from the Chakraborty et al. That obtained the constant factor approximation in classical time, but also the ideas that come into the quantum algorithm as well. There will be no quantum here, but just classic kind of mathematical ideas. Okay, so here is the approach setup, right? And this is, again, kind of a setup that is common to most of these results from the second wave. Okay, so so first of all, first kind of way to kind of reconceptualize edit distance is that, in a sense, to think about edit distance as not the number of iterations that transform one string into the other, but rather kind of its opposite, namely finding the optimal alignment between the two strings. Okay, so here is a running example. We have strings x and y. Okay, and there are many letters there, and this alignment is basically it's an injection, and it has to be ordered, like suggesting in this picture. Okay, there are these lines cannot intersect. And basically, this and a red arrow here means that, after the transformations, this and the identity of this and became this and. Okay, so this is, the notion of alignment, right? And things which are not aligned, for example, this A is not aligned, this means that it is deleted. Okay. All right, so this is, another way to think about this as, the optimal alignment is basically corresponds to the longest common subsequence. Okay, in fact, it would be exactly equal to that, right? If we are disallowing the substitutions, which don't really change the distance by more than a factor of 2, really. So think about this as alignment as the longest common subsequence between strings x and y. Okay, so here is kind of here is the actual setup. Okay, first of all, we'll be looking at substrings of x and y. Okay, so we'll call them capital Xi and capital Yj. Okay, so these are basically substrings that start at some position I and j respectively and have length w. Okay, okay, so if you think of w as being relatively large, okay, so these are long substrings, and think about this as some polynomial in n, something like n to 0.9, for example. Okay, and sometimes I'll be referring to these substrings as blocks. Okay, just easier to call them blocks. Here is one fact. This is something that is relatively folklore, I guess, that you can think about once you define these blocks, you can think about you can change from thinking about edit distance between strings x and y and switch it into the problem of finding an alignment between these blocks. Okay, so again, the edit distance between the strings x and y is basically well approximated by a minimum over all the alignments pi. Again, this is kind of non-crossing, the same property as this alignment here. And basically now, when we kind of aligning one block to the other, it's not. What it means really is that we take the block xi, we look at its matching block y of pi of I, compute the edit distance between them. Okay, and I'll have for edit distance, I'll have this subscript w here, which denotes edit distance on strings of which length are we computing. Okay, and so we compute the distance between, what we call matching blocks. We have to normalize it by W. Okay, and we sum over all blocks. Okay, so you can think about this as like doing edit distance, except that we change the alphabet. Alphabet now, is not just characters as it used to be, but blocks, right? And the distance between two new characters is the edit distance between the corresponding blocks. Okay, so this is how you should think about it. Okay, and basically, what it means is that now the goal has become that we need to find near optimal element pi between blocks xi and yj. Okay, basically, we are computing this quantity now. And for that, note that, in a sense, what we've reduced the problem to, right? I mean, what appears here, most importantly, is this calculation of edit distance on strings of length w. Okay. Okay, so think about now, kind of, in a sense, the simpler question of we need to find the edit distance. So we want to minimize this alignment, but the only thing that we care about, right? I mean, it's counting as cost is the number of times we compute. We computed the distance between strings of length w. Okay, so the question becomes is, well, how many oracle calls, if you wish, we need to do to compute edit distance between blocks of length w. Basically, how many of these xi's will compare against these yj's? So this is the goal, right? I mean, and again, xi is the block of length w. Okay, so naively, what we can do is we can do the compute all. Right? What does it mean? Is like, well, we have n squared. So let me backtrack maybe once. Okay, so we have naively we'll just compute every xi against every yj. Right, there are n blocks, n starting positions for I, and ignore the board issues for now. I mean, they're not really an issue. Okay, so we have n xi blocks, we have n yj blocks, and we compute the distance of length w, between each pair. There are n squared calls. Well, now the runtime, what will be the runtime? Right? Like, well, to compute the edit distance between strings, to compute one such oracle call, let's say we use the standard edit distance algorithm for that, takes time w squared. Okay, so this means that the runtime now became n squared times w squared. Okay, this is worse than we started doing, right? I mean, just to make sure. Okay, so this is not good, but hopefully we can save somehow else. So here is idea 0, right? So this is idea 0. I call it because it really appeared kind of in our works, kind of in previous papers on edit distance as well. Kind of it's a common idea. Is to say, well, why did we define these blocks, right? Well, these blocks are very overlapping, right? If we consider all the possible blocks, x, capital X starting at position 1, starting at position 2, starting at position 3, well, they have a big overlap. So in a sense, they kind of they repeat the information in a sense, right, a lot of times, right? So this is not very efficient, right? And in some sense, there is a reason why I defined the blocks, right? I mean, that somehow we want to cluster the information or kind of the operations of a distance per blocks, right? So it is normal to say, well, let's take non-overlapping blocks. Okay, so here is x. Let's consider this. So the non-overlapping blocks means that take x1, it's of length w. Okay, so when we take the next block, starts at w, w plus 1 formula, I guess, right? Also of length w here, right? And then the next one and so forth, right? So we do this in x, we do this in y, and we got our blocks, right? So let's just focus on those blocks. Maybe it is enough to look at those blocks. Okay. Well, the issue is that well, when we look at, let's say, x1, okay, and we look at its matching block yj, well, maybe there are like a few insertions that we had to do here. Okay, which means that the matching block for x1 starts, basically where this red arrow shows. Okay, so this, or put differently, that j, which is pi of I, kind of, for I, which starts are of blocks x, are not multiples of w. Okay, and usually they want. Okay, So, well, here is kind of one way to do this, right? And it's an idea that has been used, and basically, this is the idea that solved this issue kind of in a number of papers, but at a cost. Namely, what you can do is you say, well, let us round this J's, right? To say, let's just in Y. So it's a little bit asymmetric here, but in Y, we'll not be looking at completely non-overlapping blocks, but we'll be taking a bunch of blocks that are somewhat overlapping. In particular, let's consider all the Y blocks that start at integer multiples of delta W. Okay, where delta is some small parameter, and the effect of this is that the cost of this will be an additive delta and error, right? And this comes from all these roundings, right? And it's not hard to kind of to prove using kind of standard edit distance properties, but you can do this rounding, and this will be the additive error. Okay, so pictorially, we'll in Y will not be looking only at these blue blocks, right? But we'll also be looking at green blocks and these purple blocks, right? And this is, basically the picture here corresponds to the case when delta is one third. This means that, in a sense, the blocks are 1/3 overlapping. So I guess 2/3 to be precise. Okay, so this is what it does. Okay, but and again, that fact that I mentioned in the beginning that you can look at the matching blocks, right? It is enough to look at the non-overlapping blocks, or in this sets kind of non-overlapping blocks, or slightly overlapping. It's still enough, right? There's still enough information to basically capture and compute the edit distance between original strings X and Y. Okay, so it is enough in a sense to just look at X1, find its match, XW, find its match, X2W, find its match, and so on. Okay, so what is the cool part? Well, the cool part now is that, there are many fewer blocks to worry about. In particular, there are n by W blocks in X blocks. There are n by W delta of Y blocks, right? A little bit more by a factor of 1/delta. So this is, again, if comparing all blocks against all blocks, but non-overlapping ones, right? Then the number of calls becomes, basically product of these two things. And basically thinking of delta as being a constant, right? I mean, let's just think of delta as being a constant for now. The runtime becomes basically n squared. Okay, because there are n by W times n by W calls. Each call takes W squared time to compute the edit distance. The runtime is n squared. So we still did not improve much, right? But at least we're not doing, worse. Okay, it's some progress. Okay, I should mention that we are talking only about how many calls do we need to do to the edit distance, basically to computing edit distance on these shorter blocks and shorter substrings of length W. Okay, but of course this is not the entire problem. At the end of the day, we need to match them, right? And the matching also takes some time. But let me solve this under the rug, because this is kind of looks much more similar to the standard dynamic programming. So it is possible to basically solve it, finding this alignment between blocks now in time, which is product of the number of blocks, right? So again, n by W times n by W delta. Okay, and note that this time, this is 12 times, so it will be basically n squared by W squared. This does not call edit distance anymore, and so forth, right? So if you think again of delta as being relatively large, like n to 0.9, then this time is actually very small. This is becomes n to something like 0.2 maybe. Okay, when W is very large. So this is not a concern at all, actually, right? Solving this dynamic program. Okay, it's it's not exactly the same as for edit distance with some modifications, but reasonable modification. Okay, but we're still at the level that the number of calls did not reduce sufficiently, right? And the runtime still is n squared. Okay, so how do we reduce the runtime even further? Okay, so again, the goal is to reduce the number of calls, of edit distance calls between all xi's and yj's. Okay, and this is where the approximation, will start. All the previous things that I mentioned, have some losses there, kind of, right? But they all can be kind of small, kind of something like 1 plus epsilon. This is where the actual approximation comes in. Okay, so first, let us focus on the problem that it is enough to find close matches. Okay, so I'm slightly oversimplifying what we need to do here. But it's not. Yeah, I'm not really hiding kind of anything major. It will be okay to find xi, and for each xi to find its match y of pi of I. Basically its match under the optimal alignment. And we need to basically just, detect when it is close, right? Close means that it is a small edit distance, smaller than certain threshold. Okay, and what this allows me to do is to think about blocks as being either close or not, right? So this is not quite true because different the notion of closeness is not transitive, right? But think for now that this is transitive. So here's idea one. The idea is to use basically geometry of edit distance. This is very cool. This is specific to edit distance, some other variants of kind of sequence alignments kind of problems as well, which are distances. But we crucially use here that it's a distance. It's a kind of geometric or metric property of it, right? And this is idea number one, right? And again, this idea appeared kind of in both papers, kind of the classic and the quantum. Okay. Okay, so how do we use this triangle inequality? Okay. So here is the picture, and now I replaced. So this is not with the original strings, but these are the blocks, right? These are and think about them as non-overlapping. Just for simplicity, these are the non-overlapping blocks. And these are capital letters now because a capital letter corresponds to an actual block or substring, right? And basically, they are the same if they are close, and they are far. The distance is large if they are different capital letters. Okay, and these gray arrows are basically the alignment, the optimal alignment between blocks. Okay, so of course, when we run the algorithm, we don't see this alignment. So let us erase it here. And see how this triangle inequality idea comes into play. Okay, suppose there is some yj, okay, and this will be our yj. Okay, this a. Okay, we just took one yj and said we compared it against all the other y's. Okay, using this close to edit distance. Okay, and discovered that it is close to many other blocks. Okay, so in particular here it is close to this a as well and this a as well. Okay, and some other a's, because there is an a here, another a here, and so forth. Okay, right. So we call this set Cj. Okay. So now, suppose there is another xi. Okay, that we look, right. So this is the xi. We want to find its match. Okay, we want to find basically its match. Okay, which is the first letter in the ananas. Okay, so what do? Well, we say, well, let's look at this yj, right? We will think about this yj as some kind of center, right? Because we've computed some extra information for it. Okay, so we compare it, right? We discover that it is close, right? And they say like, well, now by triangle inequality, we can deduce that if this is, these two things are close, and this a and this a are close, this means that this is close to this, and this is close to this as well, right? And as well as this one and this one. Okay. But we need for these, we need to compute only this edit distance and the green ones, of course, right? But basically, for all these letters, for this a and for this a and for this a, right? We just need to compute to the center. And again, here we just need to compute to the center to deduce all the other similarities as well. Okay, and this is kind of the beauty of using triangle inequality. Okay, that in a sense, once we pre-process this yj, computing an xi which is close to it, we can deduce from that a lot of other close pairs. Okay, now this is we deduce close pairs. Look, we don't know which one of them is optimal, kind of, right? But we want to find all possibilities where that optimal matching, right, this xi and its match can be, right? So for example, here in this a, we compare to the center, even though this is not in its optimal matching, right? But we've deduced that this a is also close to this a here, which is, it is its optimal match, right? So in a sense, we will have computed the distance between, this corresponding this xi and its optimal match. Okay, so that's cool. Now, I should say that this is the place where the approximation tree appears. Okay, this is the one place where the approximation tree appears, right? All the other places, the approximation can be made as close to 1 as possible, basically 1 plus epsilon with polynomial in 1 over epsilon factor losses in the runtime. Okay. Yeah, so that's what I wanted to say here. Okay, so now what would be the idea, right? Well, the idea is now the following. Well, let's just sample a bunch of these centers yj. Okay, we can't sample too many because for each of them we need to compare to every other y. Okay, but let's sample something like root m, right? Where m will be here up here. We'll say that m is the number of blocks, which is basically proportional to n divided by w. Okay, so the number of calls now will be order of mk. Right? There will be for each center y, we need to compute the distance to every other, to do the oracle call to every other block in y. And we also need to compute for every center, we need to compute the distance to every x block as well. Or for every x block, we need to compute the distance to all these centers. Okay, so there are basically 2 mk calls, right? So this is how many we have. So order of mk. Okay, fine. But what is something must fail here, right? Like it can't solve the entire problem, right? In particular, we take only root m centers. Well, the issue is that this fails for fails to find the close match, right? This is what it means to fail, right? Fails for x's, which we'll call sparse. Okay, where this set basically, so we have some xi, okay? We have its match y, see? So if we look at all the other y blocks which are close to its match, right? Suppose this is very, very small, okay? And in particular, think about this s here, right? So look at this s, for example. Okay, and suppose s does not appear anywhere else in the string, right? If we sample the centers in y, we're very unlikely to sample this s, right? It's just 1 out of m, and we sample only root m such centers. So it is very unlikely that we'll sample this s. Okay, so this means that for this, for this character, this operation, basically, this, triangle inequality kind of deduction will not work, right? I mean, it won't be able to find this s kind of, right? Okay, so right, so another way to put it, kind of, right, or to think about it, is that the sparse x's, right, sparse xi's are those which are close to very few ij's. Right? In particular, if we sample k centers, right, if it is close to much fewer than m divided by k of yj's of y blocks, right, this means that it's very unlikely that any of these yj blocks which are close to xi will be sampled as a center, and therefore we will not detect that xi is close to its match. Okay, if it is much larger, it's something like larger than n divided by k, maybe times log n, then with high probability we'll sample a center which is close to xi, right, and deduce that xi is close to its match as well. Okay, so the remaining, this is why we'll need the next idea. The remaining issue is to how to deal with these sparse xi's. And again, sparse xi's are those which are close to few blocks in y. Okay. So here is idea 2. Okay, and okay, this will be the 2 ideas, right? And this idea again, this is the idea where in the quantum paper, it was the quantum, but we also can do it classically. Okay, and this idea is kind of, if previous idea 1 was kind of more like geometric idea, right? It's like it was, we're using triangle inequality. This one is more combinatorial kind of idea, and it's like a little bit closer to the kind of edit distance structure. Okay, and here's the idea that neighbors have neighboring matches. Okay, maybe it's like neighbors have like similar preferences, I guess, right? I mean, here it is like neighbors have neighboring matches. Okay, and what does it mean? Kind of pictorially, you can look at these arrows here, and you see that they are basically have the same angle in a sense, right? As in, once there is kind of a string of things which there are very few edit distance operations, then these arrows, these gray arrows, will roughly have the same angle between them, right? And if this A matches to this A, right, then the next N will match to the next N and so forth. Okay, so let us formalize this slightly more. So I mean, this is what I just said, right? If the block xi matches to some position j in y, right, then likely the next non-overlapping block of x will match to the next overlapping block of y. Okay, maybe there will be some edit distance operations where a little bit, right? I mean, maybe it's, plus minus here, right? This is why this is approximately, right? But it shouldn't be much far off unless there is a lot of edit distance operations happening right there. Okay, so here is how we can use this, right? And this is slightly more formal than I said so far. Okay, fix some sparse xi. Okay, so consider some xi. Okay, so this is kind of the first sparse xi that we look at. We don't really have much information to kind of go on for, right? So we'll have to check for that particular xi. We'll have to check against all possible y's, and we'll find, all the yj's which are close to it. Okay, but in a sense, the good part is that after we've done this, okay, if we define set si to be all the y blocks which are close to xi, there must be few. This was the definition of sparse xi. Okay, this is the xis where the sparse xi was precisely the block x which is close to few y blocks, right? So few means, of the order of n divided by q, right? Total number of y blocks divided by the number of centers that we chose at random. Okay, cool. Right, so we didn't manage to save any number of calls here. So xi was still compared against all y's. But we can use the information or the work that we've done here to benefit other sparse blocks, right? So this is kind of the idea. So in a sense, one neighbor kind of does the work, but it, one block does all its work, all the work, but then its neighbors can reuse that work in a sense. Okay, so okay, so in particular, if you look at the next block, right, which is xi plus w, right, and let's say this is sparse, okay, and we need to find the match. Well, it is okay to look basically to compare only to the neighbors of right. So the j was right. So we found si which are the close blocks to xi. Okay. So what we need to do is for every j, which is a potential match for the block xi, we look at its neighbors, and that should be the potential match for our neighbor xi plus w. Okay, so think about this as, like maybe you're putting, a cable for electricity, going to a neighborhood, right? It's like, once kind of there is like one big cable kind of coming to the center of the neighborhood, kind of, right? The local neighborhood, just needs to add a little bit of cable kind of to do, to connect to that, main cable leading to the neighborhood. So the same here, kind of, like this is kind of the main work, right? I mean, the other neighbors are kind of piggybacking on the work that has been done before. Okay, and maybe the next xi plus w is not sparse. Maybe it is somewhere further down. Okay, and just to conclude, the point here is that for the neighbor, the number of comparisons that need to be done is only proportional to the number of neighbors of si, right? Which will be of the order of the size of si. There is a delta dependence because, again, the y blocks are a little bit overlapping, right? So, one has to be careful what it means to define neighbors, but that's basically it. Okay. Okay, so again, suppose, the next block, xi is sparse, but maybe the next block is not sparse, right? I mean, what do we do then? Kind of, right? The next sparse block is somewhere down the line. It doesn't have kind of a neighbor right next to it, which is sparse, which done all the work. Doesn't have to do the work from scratch. That would be bad. No, and yeah, apologies. I forgot to mention one point here that the neighbors have neighboring matches kind of is a statement which is on average, right? Because it could be that, pictorially, this was an S, right? I mean, this was the S, right? Suppose this S has done all the work of comparing against, all the blocks here in Y. Kind of, it found that, okay, I have one match here. Okay, well, when we want to compute which are the potential matches for this exclamation mark, well, it can look just around S, right? And, find this match here, right? It doesn't need to look here anymore. Okay, but it could be that, maybe, this exclamation mark was not here, but maybe it was here somewhere, kind of, right? And there is like some, garbage basically here that needs to be deleted, and the actual match is here. What do we do then, kind of? So Well, first of all, there are kind of two things, right? I mean, if there is a lot of error here kind of happening, then, we can kind of give up on this exclamation mark and basically amortize it against this error, right? And say like, well, there is a lot of error happening, right? It's okay, some of these things which are close to a lot of errors, like this exclamation mark, we will not be able to compute the match, introduces some error, but again, very controllable. Okay, but suppose there is, some exclamation mark here, let's say, right? And here, so this two. And this is the next parse, right? So there is this S, which is sparse, and there is a exclamation mark, which is sparse here, right? Which is much farther away. It doesn't have a sparse neighbor. What do we do then? Well, even if we take some string block, right, which is somehow further down, right? Let's say it is Z positions away. Remember that X blocks are non-overlapping of length W. So let's take one which is Z positions away, right? Where Z is big number. Okay. Well, what we can do is we say we can still try to use basically we'll call it extension, right, from this S. Okay. But now instead of looking as just neighbors of S, right, we need to account that, well, this exclamation mark here is a distance Z here, right, from this S here. This means that in the Y block right here, this distance should also be order of Z. It cannot be much more than order of Z, because otherwise this means that there has been too much error happening kind of in this area. But if there isn't, right, then the distance between this S and exclamation mark in X should be not that different from the distance between S and this exclamation mark in Y. Okay, so this means that now we need to look at more neighbors of positions in SI proportional to Z, which potentially can be much larger than proportional to SI. But the cool part is that on average, over all the blocks from XW to XWZ, so there should be I plus W and XI plus WZ. Okay, all the blocks in between, remember, all these, things that are covered by 3 dots were not sparse. So we didn't do any of these operations, right? So we can amortize the operations that we do here to all these Xi's which are in between. And on average, like the number of things here is Z, right? And the amount of kind of overhead in the runtime is also proportional to Z, just by how many neighbors of SI we consider. So this means that on average, we still have order of basically SI per block XI of this comparison to the neighbors, right, of calls. Okay. The conclusion of this discussion is that now for every XI sparse, on average, the number of calls to the edit distance that needs to be done is order of the size of its kind of Y blocks which are close to it, right? Which we said by definition of sparse is only proportional to MK. Okay, so this means that the larger number of centers we take, the fewer calls we need to do. Okay, so just to put all this together, kind of implementing idea 1 plus 2. Okay, idea number 1, and again, we're counting the number of calls to the edit distance of strings of length W. Okay, so from the first part, we said like if we take K centers, the runtime will be MK. From the second part, it will be, I said on average, it's MK per block XI, right? There are M potentially blocks of XI. Okay, it will be basically M squared divided by K. Okay, and again, taking K, which is equal to root M, basically, whatever optimizes the summation, we get this. Again, remembering that N divided by W is the number of blocks, which is N. Okay, so basically these two ideas reduce the number of calls to be basically N by W to 1.5. Okay, this is kind of the actual improvement that happens. Kind of right. Previously it was quadratic, now reduced to a power which is 1.5. Okay, so this is ideally there are some challenges really. Okay, so like a lot of these things on average kind of right happening, but I guess slightly kind of slightly more serious kind of issue still solvable is that it could be, remember that we started with some anchor xi, right? We say like, well, here is an xi which does all the work, and then it kind of, helps the neighbors as well, kind of, right? Once you've done this name, kind of, right? The other neighbors can basically extend from it or piggyback to it, right? But it could be that sparse anchor xi that, we started with, right? Has too much error. It doesn't have a close match, or we don't find the match. Right? So this means that it can help the other blocks, and we don't really necessarily know that this is the case even. So one has to deal with this kind of issues. Okay, and it's possible. So the original Chakraborty et al. Paper, had one way to deal with this, right? And this is basically the runtime as a function of delta that we obtain for constant multiplicative approximation and additive delta n approximation. I also had, I guess shameless plug, I also had, basically a write-up, after seeing their paper, trying to simplify the algorithm a little bit, right, that achieves slightly smaller runtime. I guess the dependence on delta is worse, but on n it's a little better. But I guess more importantly, it really kind of is an algorithm that pretty much puts these ideas, can implement this idea 1 plus 2 together, as I described in the previous 2 slides. And the idea is basically like, well, this can happen, but if we sample many of these anchors, then, some of these anchors, should be good, kind of, right? I mean, cannot be in this situation, right? So this is basically the idea. And, the sampling has to go in the right order. So, let me just, kind of quickly, say how this is done, right? But, if you're curious, kind of, right, and you want to see like a kind of, in my opinion, the shortest algorithm kind of, to solve edit distance up to constant approximation in sub-quadratic time, take a look at the paper. It's just, a few pages long, really. So here's how you do it, right? You think about dyadic tree. Okay, so a tree where, the root is the entire all the blocks, right? Then you split them into first half, second half, and so forth. Okay, and so this is how we proceed. So in each node of the tree, right, which corresponds to basically a sequence of these blocks. Okay, we sample log n of these random anchors, right, which basically these kind of anchors, and store their set Si of closed Y blocks. Again, if there are too many, this means that it is not sparse and so forth, right? I mean, there are some, some differences, right? But, non-substantial. Okay, so think about that. They are sparse, and we store their sets Si, which are, relatively small. Okay, so now once we do this for one level, we go to the next level of the dyadic tree. And for every node, we again sample the anchors, and we do this extension, but we do the extension from the anchors of its parent. Okay, so the extension, just as I mentioned on the previous slide, the second option, you do that kind of extension, but using the anchors which are in the parent of the current node. Okay, and the main claim is that at least anchor, basically kind of in this tree, at least for in every node, at least one anchor will succeed in a sense that it will contain its matching block y of pi I in this set Si that it stores, unless this sequence of blocks is mostly composed of dense blocks, in which case the dense block approximation is already good enough, and we can basically give up on the sparse blocks, right? It won't introduce too much error. Okay. I should say that independent paper obtained runtime which is clean n to 1.6, basically removing the dependence on delta, and part of one of the idea there is to use the Ukonian and Myers algorithm, to run faster when delta is small. And I should say that why this is n to 1.6, not to n to 1.5, as I mentioned, because remember the results of the dynamic programming, the second step that we need to run. And this is kind of, combining the two together, choosing the optimal W will give this runtime, which is a little bit more than n to 1.5, right? And it is a great open question, to see, can we obtain basically time, which is n to 1.5, for in this case, right? I mean, I should mention that this in particular these two papers obtain approximation which is 3 plus epsilon, and it's a great question to see if we can get 3 plus epsilon approximation in time which is n to 1.5. I mean, sounds plausible, but we don't know how. Okay, as I already mentioned, these other two papers in 2020 improved the number of calls to this oracle. Okay, so improved this n to 1.5 exponent to basically 1 plus epsilon, but at the cost of additive error term. Okay, so these are, I guess you can think of, this was, basically the main kind of algorithmic techniques that I wanted to mention. And now coming kind of to the paper with Negev Shekel Nosatzki, where basically, using these ideas and some others, we obtained a runtime which is n to order of n to 1 plus epsilon for constant approximation. Without any additive error. And there are a few differences that I'll highlight, right? But I won't really go into the detail of this algorithm because it is much, much more complicated. But, let me just say kind of, I guess, a few ideas that kind of are different from the approach that I mentioned so far. Okay. All right. So one kind of, and structurally kind of the difference is the following, that instead of having these oracle calls to the edit distance of length w, which by the way, to kind of improve the runtimes, you can always replace, recursively with the algorithm that you just got, that improves the runtime somewhat, right? So here we will kind of do away with calling the oracle, but instead we'll use what is called a distance oracle, which is a data structure, which kind of captures the same information, but instead of going, top bottom, right, it goes bottom up. Okay, so let IW be all the strings of length W. Okay, so these are all the blocks, right? Again, forget the non-overlapping aspect, right? We're back to overlapping strings, substrings, blocks. Okay, we'll build a data structure. Okay, so for fixed W, and W goes from shortest strings of length 1 to n to the epsilon to n to the 2 epsilon, so forth, until we take substrings of length n, which is basically the entire strings. Okay, so for each W, we build a data structure such that for every 2 strings, you can query and say, like, well, for this string, for xi, let's say, and yj, what is the edit distance between them? The oracle will spit out a number, which is an approximation to the edit distance between these. We have some caveats, right? This that I'll get into a second. And the query time takes time, which is n to order epsilon. Okay. Most importantly, this is much smaller than W potentially. W at some moment will be something like 210, right? So the query time will be much, much smaller than even the length of the blocks. Okay. So this is called a distance oracle engineering. Okay. So here is kind of the big pictorial view, kind of, right? I mean, we start with distance oracle for strings of length 1, right? We call this D1. Well, basically, what does this mean? This is basically the metric of Hamming metric on the original alphabet sigma, right? So are the 2 characters equal or not, right? If they are equal, then the distance is 0, right? If they are not equal, distance is 1. Okay. Out of that, we'll build the distance oracle for substrings of x and y of length n by n to the epsilon, n to the 2 epsilon, and so forth, until we get to strings of length n, which means that once we have this, we just query this last distance oracle on the block starting at position 1 of length n in x and y. These are exactly the strings x and y. This should give us the edit distance. Okay. Now this approximation, I'm slightly lying here. It will not be approximation in the kind of usual sense of approximation, but for every position, for every substring I and j, we give this, let's say, constant factor approximation. In fact, we cannot do that. Okay, for us to be able to build such a data structure, we would have to basically query all possible I and j. Okay, there are some examples where basically you cannot avoid that, right? I mean, there is, in a sense, to describe the metric, you roughly need n squared information. You cannot, you cannot, you cannot store it in less than that information, right? So building this data structure will take too much time to access all that information. So the oracle, this distance oracle, will have a slightly relaxed guarantee, which you should think about as like just enough for us to approximate the edit distance. In particular, this approximation will be up to a constant, and it will be on average over the blocks for the optimal alignment pi. Okay, we'll see this guarantee again on the next slide. Okay, but for now, let me just dig into the, in a sense, kind of one of these arrows, right? So we want to say like, well, we want to go from distance oracle on strings of length n to the epsilon to the distance oracle on the strings of length a little bit more and to the 2 epsilon and to the 3 epsilon, to the 4 epsilon, and so forth. And we want to do this in time which is n to 1 plus order epsilon. Okay, so quickly, and this is the last technical slide. Again, there will be 2 components, and in a sense, this will be kind of corresponding to the, if you wish, 2 ideas or 2 components of the algorithm that I described before that. Namely, part 1 will be the dynamic programming aspect of it, right? So what it does, it says, well, I have a distance oracle. We call it alignment distance oracle. Okay, it's basically kind of a procedure that takes that has access to this distance oracle for strings which are shorter of length w by n to the epsilon, and builds given this distance oracle can spit out that for any given ij can spit out basically the of length w can basically spit out the number which is an approximation to the edit distance between ij. Okay, so it basically builds the edit distance from blocks of length, shorter blocks to longer blocks, and this is done in programming. It will run in time which is basically n to 1 plus epsilon. Okay, and in time n to the order epsilon per n to the epsilon time per query per ij. Okay, okay, and also same number of calls. Okay, and the other part is kind of using the triangular inequality kind of aspect. This is much more complicated here. We call it matching algorithm, right? And basically builds the distance oracle from this block, right? So in a sense, what's happening here, right? Like, well, this box, to compute, to approximate the distance between given I and j in this square block, right? It uses recursively this triangle, right? This distance oracle for shorter strings, right? Now we want to break the dependence and basically build a distance oracle for longer strings, which does not use this recursively. Okay, otherwise, we will not be saving any time. Okay, so for this, we'll use something called matching algorithm that builds a graph that approximates this alignment distance. Okay, and kind of slightly more formal, and I'll get to it in a second. The distance. So what does it mean for the graph to approximate the distance, this metric? Well, it is a graph that captures the entire metric, alignment distance, for all the blocks. Again, remember 2 n blocks. Okay, this IW, such that the shortest path distance in the graph. Let's say we want to compute the distance between this, each node corresponds to a block, right? We want to compute between this one and this one. Say like, well, it is the distance in the graph, the shortest path distance. Okay, and it approximates this alignment distance again in a similar way, like we mentioned before. Okay, so then you build a graph, and out of the graph, you basically use kind of slightly more use standard techniques to transform the shortest path on the graph, which is sparse for me, into a data structure, which for given I and j, quickly basically tells us whether, what is the distance, right? And you should think about this as kind of is dimension reduced metric IL. And this is, again, part which uses a little bit more kind of geometry. In particular, here we're using constant factor approximation of Matushek into L infinity. Okay, but I won't go into detail, but it's and it's kind of not a very fancy result, but just wanted to highlight kind of, right, using kind of more theorems or kind of more statements from geometry, right? Like we usually use for high-dimensional geometric algorithms. Okay, and just to kind of go a little bit more in detail what it means to be approximate. Here is kind of a little bit more formal. We build a, it's enough to build a graph for a one scale C, just like in the previous algorithm I mentioned. And basically it has the following kind of two guarantees, right? This approximation kind of in two directions, right? One is that if there exists an edge, okay, and this is, this corresponds to 1. Okay, this inequality, right? It says that if there exists an edge, right, this means that the alignment distance between this I and j is relatively small, right, proportional to the scale. On the other hand, we want to, to have this statement in the other direction, right? That the distances in the graph do not distort the distances too much more than the alignment distance. Okay, so what we would like to say is that the alignment distance is small when the distance in the graph is also small. Okay, so that there exists a two-hop path in the graph. Okay, so the distance in the graph did not increase too much. Okay, now we can't do this, right? This is exactly the same issue as I mentioned before. That just alignment distance metric just has too much information. You cannot just capture it with a sparse graph. Okay, so we have a relaxed guarantee, which is just enough, namely that the alignment distance. What the guarantee will be that the alignment distance for every xi and its match yf by a is at most c when we have a two-hop path, and this holds for any alignment pi, including the optimal one, for all positions I, except for i's which are proportional to the error amount. Okay, so this is kind of this very average kind of notion. Okay, and property 3 is that the amount, each of these steps will take time, which is n to order epsilon, and overall when you put everything together, the runtime will still be n to the 1 plus order epsilon. Okay, so let me conclude. Right, so finally, that I guess the main statement that we wanted to state here in the talk is that you can compute the distance in constant time in runtime, which is n to 1 plus epsilon. Okay, so this is sequence of a number of papers now, but it's a very nice result, right? I mean that we can do this, right? I mean, starting with paper by Chakraborty, who showed just sub-quadratic time. It's already possible for constant approximation. Okay, and maybe one message here, kind of to remember is that some of the ideas here are naturally geometric, right, or metric, really, like triangle inequality, for example, or this like Matushik embedding, right? And maybe it's something kind of one of the morals, right, that the geometry is helpful even for problems that look very combinatorial, like edit distance computation. Okay, there are many related work, kind of related, especially kind of spurred by the Chakraborty et al. Paper, and many open questions remaining, right? So as I mentioned, there's I didn't write out all the citations. You can follow the link here at the bottom to see what are the citations if you are curious to take a look at those papers, and I definitely recommend you to. So let me just state the remaining some of the open questions that I find interesting. One is, what is the smallest approximation in linear time? Okay, so even in this time, what is the smallest approximation, right? So what is our dependence on epsilon? Our dependence on epsilon is doubly exponential. Okay, so it's really bad. It's like 2 to the 2 to polynomial in 1 over epsilon. Okay, it's reasonable to without kind of doing substantially different things to obtain something which is potentially even polynomial in 1 over epsilon approximation only. Okay. Okay, so this is kind of question 1. So double exponential improvement may be possible without kind of major changing majorly the things. The other kind of way to look at it is to say, like, well, how about I want to obtain sub-quadratic time algorithm, right? But I want the smallest approximation as long as we get some sub-quadratic time algorithm. Okay, so in particular, the natural kind of number to look at is 3, right? Approximation 3, as I mentioned, this appears from the triangle inequality. Okay, so for approximation 3 plus epsilon, right? The epsilon appears, from all these other approximations that I mentioned. Okay, so the current best runtime for this is n to 1.6, and as I mentioned, it's natural to think, to consider obtaining n to 1.5, maybe even more, kind of, right? But n to 1.5 is, it's kind of natural, natural barrier in a sense, right? So can we at least reach that barrier? Okay, and again, as I mentioned, 3 kind of is a bottleneck because it comes from using triangle inequality. So once you use triangle inequality, factor 3 appears. It's natural to say, like, okay, maybe we can do something else. Maybe we can improve upon the factor 3 approximation. This is also a very exciting question. Nice result, a recent result showed that you can get actually approximation a little bit less than 3, as long as you have a large additive approximation. Or put differently, when delta is in the constant regime, then you can get a little bit better than approximation 3. Another, kind of direction that has been again kind of renewed kind of recently is to look at sublinear time algorithms. Let's say I am okay with higher approximation as long as my time is even less than n, right? So I don't even read the entire strings, but I just sample them in different positions and somehow deduce whether the distance is very large or very small. Okay. Another related question is, well, how about computing or approximating longest common subsequence or longest increasing sequence? Now, this is not a metric anymore, but it turns out, as some of these papers have shown, that you can use similar ideas. There is some kind of, LCS version of the triangle inequality where, it still kind of can, do these deductions. And improve the runtime as well. So get better algorithms there. And finally, kind of a set of related questions is to go beyond just computing distance between 2 strings x and y, but let's say you have a text versus a pattern, what is the best trade-off between runtime and approximation. There has been some work there, but I don't think that at the moment we know kind of the best possible, even just using these results. Okay, and I'll end here. Yeah, thank you. Thank you for watching. And let me know if you solve any of these questions. But I'll be very, very happy to hear. And good luck.